The composition of soil plays an important role in farming. The techniques of spectroscopy were used to analyze soil samples from Zone 5 in order to determine whether the cobalt, copper, and nickel content was optimal, too high, or too low. The data collected by this group suggests that the cobalt, copper, and nickel levels of the soil of Zone 5 fall within the specified limits. However, data collected by other groups suggests that Zone 5 suffers from an extremely high nickel concentration. Therefore, more research must be done to determine the safety of the soil in Zone 5.
Every agricultural venture depends on a solid understanding of chemistry. This is especially true regarding the composition of the local soil, as farmers need to both know the types of elements most abundant in their land and how to change it if necessary. The lack of certain elements such as nitrogen can hamper plant growth, and the overabundance of others such as copper can even kill livestock. In order to develop a knowledge of a particular field or zone, we can use a spectroscopy to precisely analyze soil composition.
As we have learned during the Lab 2 cycle, the absorbance and the transmittance of light through a given substance is related to its concentration in a solution of it and water. Moreover, the absorbance of light within a given substance is directly proportional to its concentration in a solution. As such, a SpectroVis Plus spectrophotometer was used to measure the absorbance of the visible spectrum of light within a given concentration of a sample. Other equipment used in this project included 3.1 molar standards of cobalt, copper, and nickel, 2 5 milliliter graduated pipettes, 2 pumps, and 7 cuvettes.
Calculations were performed to determine 7 different concentrations of 3 elements, CO, Ni, and Cu. 7 5 ml solutions of these concentrations were prepared for an element with water, with the 7th concentration simply being 5 ml of the standard. After proper calibration, each concentration was analyzed using a spectrophotometer, and the absorbance was measured at the determined wavelength. The determined wavelength was the most absorbed wavelength, or lambda max, of the first concentration measured. The absorbance at the lambda max was then recorded in a data table along with the lambda max and the concentration of the given element in the solution. A graph of absorbance versus concentration was constructed, and a line of best fit was drawn in order to produce an equation relating to absorbance and concentration. This process was repeated for each element.
Here, we have the derived equations used to find the unknown concentrations in molarity and their equivalents in milligrams per kilogram, respectively. The linear equation relating absorbance and molarity was found using a spreadsheet software. Using the tabulated data, an equation was found relating absorbance to cobalt concentration. The equation that was derived was absorbance equals 5.50 times molarity plus negative 0.00921. The unknown concentration of cobalt in Zone 5 was found to be 0.079 plus minus 0.002 molar. From the tabulated data, an equation was found relating absorbance to copper concentration. The equation that was derived was absorbance equals 7.94 times molarity plus 0.035. The unknown concentration of copper in Zone 5 was found to be 0.143 plus minus 0.002 molar.
The nickel results, we found an equation relating absorbance to copper concentration. The equation we derived was absorbance equals 7.24 molarity plus 0.0152. The unknown concentration of cobalt was found to be 0.0061 molar.
On this slide, 3 tables are shown, relating the data collected by this group to that collected by the class as a whole. As opposed to the previous slides, the concentrations here are expressed in milligrams per kilogram. In the uppermost table, each element, their upper and lower limits of safe concentration, and the quantity present in Zone 5, according to this group, are displayed. This data was used in filling out the rightmost column. As each metal was found to be within the proper bounds, each concentration level in the soil was determined to be safe. Of course, yes here means that the metals are within safe concentrations, and high and low are shortened here for brevity. The next two tables display each group's reported values for the unknown concentrations and their levels of safety as per the limits shown in the uppermost table. Since multiple groups measured concentrations from the same zones, each zone was divided into an A group and a B group. The blank cobalt value in the middle table was omitted as per direction by the lab instructor. For each group and zone in the middle table, the only element outside of the safety limit was cobalt, and for each team and zone, the cobalt concentration was too low. The bottommost table saw a higher degree of variation in safety results. The levels in Zone 4A are all within the proper limits. The copper and nickel levels in Zone 4B are within the proper limits, but the cobalt level is below the lower limit. The copper and nickel concentrations in Zone 5A are above their upper limits, and the cobalt level is within the upper and lower limits. This team's data is restated in Zone 5B, so there is no need to review it. The cobalt and copper levels are within safe limits in both Zone 6A and Zone 6B. And while the nickel level in 6A is also safe, the nickel level in 6B is above the upper limit. Based on the data collected by this group for Zone 5, the concentration levels are safe for all three metals. It may be wise to monitor the copper levels in Zone 5, however, as its concentration of 0.454 milligrams per kilogram is approaching the upper safety limit. Regarding the concentration levels of each zone, the cobalt concentration in Zones 1, 2, and 3 all need to be raised to a level within the upper and lower limits. Zone 4 would also benefit from a higher cobalt concentration. It is also wise to decrease the nickel concentration in Zone 6. The average concentration of Zone 6A and Zone 6B is 0.499 milligrams per kilogram, which is extremely close to the upper limit of 0.50 milligrams per kilogram. Regarding Zone 5, it is recommended that the zone is altogether reviewed. The two groups' reported nickel concentrations vary by more than an order of magnitude. However, if the concentration is equal to the average of the two observed concentrations, it would be best to significantly decrease the nickel concentration. Additionally, it would be wise to decrease the copper concentration in Zone 5. The average of the two concentrations is 0.483 milligrams per kilogram, and since there is no lower concentration limit, and one of these values exceeds the upper limit, it is recommended that the concentration be decreased. Here you will find the citation for the source used in the background portion of this presentation.